In this video, we're going to talk about galvanic cells, which are also called voltaic cells. So what are they? Well, galvanic or voltaic cells are devices that use a chemical reaction to create electricity. Specifically, the type of chemical reaction that they use is called an oxidation-reduction reaction, but we'll talk more about that later. Now, galvanic or voltaic cells may be totally new terms for you, but I'm willing to bet that you use these devices almost every single day of your life. And that's because a battery is an example of a galvanic or voltaic cell. There are chemicals inside batteries, and those chemicals react together in an oxidation-reduction reaction that makes electricity. And this is what powers your cell phone or your flashlight or whatever the battery is hooked up to. So let's learn more about these devices and see how a chemical reaction can create electricity. Okay, so I think for the rest of this video, I'm just going to call these voltaic cells instead of calling them galvanic or voltaic cells. All right? So I now want to talk about the parts of a basic voltaic cell, one that you could actually make in the lab. So here's what they are. First, we start with two beakers or containers of water, and into one of them we dissolve some zinc sulfate to make a solution, and then into the other we dissolve some copper sulfate and make a solution with that. So we got these two solutions. Then we take a piece of zinc metal, like this one right here, and put that in the zinc sulfate solution. And then over here we take a piece of copper metal and we put that in the copper sulfate solution. The next thing we do is we take a wire, a metal wire, and we use that to connect the two pieces of metal together. And when we do this, something amazing starts happening. Electrons start moving through this wire. They move from the zinc metal into the copper metal. Now, this is a big deal because moving electrons are what make electricity. So when we hook this wire together with the pieces of metal and electrons start moving through it, we have electricity. We have electricity moving through this wire. And what we could actually do is we could take a little light bulb like this and hook it up to this wire, and the light bulb would turn on because there's electricity moving through this wire. Now, to be really specific, there's one more part of the voltaic cell, and that's a little tube called a salt bridge that connects these two solutions. We'll talk more about the salt bridge at the very end of this video, but right now I'm going to leave it out because I want to make sure that we keep things simple. So this is the basic setup of a voltaic cell. Now, I want to zoom in so that we can see the atoms and electrons in the metal and in the solution and understand what's causing electrons to move along this wire and create electricity. Here's our magnification of the different parts of the voltaic cell. We can see some of the atoms in the metals and in the solutions. So let me show you what's what. This is a magnification of the area here. These zinc atoms are on the edge of the piece of the zinc metal. And then these Zn2+ ions are in the solution. They're part of this ZnSO4 solution. I'm not showing the SO4 here. I just want to focus in on the zinc. So, zinc ions in the solution and these zinc atoms in the piece of zinc. Then over here, we have these Cu2+ ions that are in the CuSO4 solution. They're dissolved here. And then these copper atoms are on the edge of this piece of copper here. Okay? So, we've got a wire that connects the zinc and the copper. And we've said that when we hook everything together, electrons start flowing through this wire. Well, why is that? Well, when we connect these two pieces of metal with a wire, it kind of starts a tug of war between the zinc and the copper. They're the electrons. One of them wins and one of them loses. It turns out that Cu2+, these atoms here, Cu2+ has a really strong pull for the electrons. But then on the other hand, zinc, these zinc atoms, zinc has a weaker pull for electrons. So in this tug of war, Cu2+ ends up winning. Let me show you how this happens. So Cu2+ really wants electrons. So it's kind of like it calls over here to zinc, which has a weaker pull on the electrons, and says, hey, zinc, give me some of your electrons. And zinc's kind of weak, so it's like, oh, okay. And what happens is, let's say this zinc atom here gives away 2 of its electrons. And these electrons enter the wire and move towards the copper. Now, when zinc gives away those 2 electrons, it causes its charge to change. It's lost 2 electrons, so it gets a positive charge, and it becomes Zn2+. Now, changing from neutral zinc to zinc 2+ has a big effect on this atom. And that's because neutral atoms make up solid metal, but metal ions usually dissolve in water. So after this zinc atom turns into Zn2+, because it lost these electrons, it's no longer part of the solid metal anymore, and it floats off, it dissolves into the solution. Okay, so that's what happens to the zinc. Then, over here, these electrons make their way down the wire to the copper, and one of these Cu2+ ions, which really wants electrons, is going to come over here, and these 2 electrons are going to be added to the Cu2+ ion. Gaining these 2 electrons is going to get rid of that 2+ charge that was on the copper, and that is going to turn it into a neutral atom, which means that it is no longer going to be able to dissolve in solution, and it's going to become part of the solid copper metal here. Okay? So that's what happens to the copper. Now notice that for this whole process to happen, electrons have to move through this wire, and that's where the electricity, the electron movement, comes from. Let's see that one more time. So zinc loses 2 of its electrons here. Those move through the wire. Loss of those 2 electrons causes zinc to take on a 2+ charge. It is then going to dissolve in the solution. These 2 electrons are going to move over here to copper, and one of these Cu2+ ions that really wants electrons is going to come, it's going to take them in, and that is going to get rid of the Cu2+. It's going to get rid of the 2+ charge, and this neutral copper atom is now going to become part of this solid piece of copper metal. So that is where this electron movement through the wire is coming from. Zinc loses these 2 electrons. They move through the wire, creating electricity. They come over here, and they join up with the Cu2+, turning it into neutral copper. We have these electrons moving through the wire here, creating electricity. So that is how we get electricity, from these electrons moving from the zinc over here into the copper. And if this happens long enough, we actually see these 2 pieces of metal change, right? Like these zinc atoms keep coming off of this piece of zinc, so it's essentially dissolving. And over time, what we'll see is that this piece of zinc actually starts to dissolve. It gets smaller and smaller. But then on the other hand, those Cu2+ ions are coming out of solution and are attaching to the solid copper. And so they're going to make this piece of solid copper bigger and bigger. And so if we let this voltaic cell run for long enough, we'll eventually see that these 2 pieces of metal actually change size and shape. diagrams for the process that's happening in the voltaic cell. I want to describe what's going on in terms of oxidation and reduction. So over here, one of these neutral zinc atoms is losing electrons. So that means that oxidation is happening on this side of the voltaic cell. And over here, this Cu2 plus ion is gaining 2 electrons to turn into a neutral copper atom. So reduction or gain of electrons is happening over here. Now we can give names to these 2 parts of the voltaic cell based on whether oxidation or reduction takes place. So the cathode is the name that we give for the site of reduction, where reduction happens. So reduction is happening here, which means that the piece of copper is the cathode, the site of reduction. And the piece of zinc over here is where oxidation is happening. So the piece of zinc is going to be the anode. So reduction at the cathode on copper, oxidation at the anode on zinc. Now let's write reactions for the 2 processes that are happening. Okay? First, let's write the reaction for reduction. We're starting with Cu2+, and this Cu2+ is dissolved in solution. So I'm going to write that with an AQ for aqueous after it to show that it's dissolved in solution. Now, this Cu2+ gains 2 electrons, so I'll write plus 2e minus, and that gives us a neutral copper atom. So I just write Cu with no charge after it. That shows that it's neutral, and then it's part of the solid metal, so I write an S after it. So this is the reaction for the reduction process. Over here, the reaction for the oxidation process. We start out with a neutral zinc atom. And this neutral zinc atom is part of the solid piece of zinc. So I'm going to put this S here for solid. Now it loses 2 electrons. To show that we lose something in a chemical reaction, we put it on the other side of the arrow. Okay? So I'm not going to write anything right here. I'm going to put this arrow. I'll leave the electrons for last. Losing the electrons turns the neutral zinc atom into a Zn2+ ion, Zn2+, that is now dissolved in solution. So I'll write AQ here. And then finally, to show that I lost those 2 electrons here, I'll put plus 2e minus on this side. So this is the reaction for the oxidation. Now these 2 reactions that I wrote, we call them half reactions because each one of them tells half the story of the oxidation reduction process. And we can actually give names to these 2 parts of the voltaic cell as if each one of them is half of the big picture. We call this the oxidation half cell. It's half of the voltaic cell where the oxidation is taking place. And we call this the reduction half cell. It's half of the voltaic cell where reduction is taking place. And it is these half reactions that show what's going on in each one of the half shell. In each one of the half cells. I said half shells. It's like Teenage Mutant Ninja Turtles coming back to haunt me from the 80s. Anyway, we have these 2 half reactions, and we can put them together to get a net ionic equation, which shows the overall oxidation and reduction process. We start with solid neutral zinc and Cu2+ ion, and then at the end of the process, we're left with zinc 2+ ion, and then we have solid copper. This is the net ionic equation that we get from adding together these 2 half reactions. Now, when we're talking about voltaic cells, we're often asked to represent them in cell notation, which is a shorthand abbreviation of the chemical reactions in the voltaic cell. It's a way that we can show what's going on without drawing a picture of the whole thing. Okay? Cell notation is sometimes referred to as a cell diagram, just so you know. So here's how we would write what's going on in this voltaic cell using cell notation. We start on the left with the oxidation process, okay? How does the oxidation process start? Well, I have the half reaction up here. It starts with solid zinc, okay? So I will write Zn solid right here. That's how the oxidation begins. Then I put this line here, and I show what we end up with in the oxidation process, which is Zn2+, okay? So Zn2+, and that is dissolved in water. It's part of the solution. It's aqueous. So this shows the oxidation process that happens in the half cell over here, okay? Then I put two lines like this, and these two lines represent the physical boundary between these two half cells, or you can think of them representing the salt bridge. Okay, now on the right, I put information about the reduction process. So the reduction process begins with Cu2+ aqueous, Cu2+ aqueous, and then I will put another one of these lines, and the reduction process ends with Cu solid. So there's Cu solid. So this is how we can sum up what's going on in this voltaic cell using cell notation. We have the oxidation process, and then two lines showing the boundary, and then we have the reduction process. So finally, we've talked a little bit about the salt bridge. I said we discuss it at the very end. So let me take a minute or two and explain what the salt bridge is, what it does, and why it's important in a voltaic cell. The salt bridge helps to balance out charge in the voltaic cell. Here's what I mean. The two solutions are made up of both positive ions and negative ions. I didn't show the negative ions before. Those are these yellow things. I just showed the zinc and the copper. But along with these metal ions are these polyatomic ions, sulfate, SO4 2-. It's a sulfur with 4 oxygens, and the whole thing has a 2- charge. I didn't want to have to keep using this thing, so I've just abbreviated these as SO4 2-. But the point is, the negative charge from the sulfate balances out the positive charge from the zinc or from the copper. So right here in my two half cells, the charges are balanced out. But let's look at what happens as the voltaic cell begins to run for a while. Okay? Over here, these zinc atoms are going to give electrons to copper. So they are going to end up with a charge. I'm not showing the electrons here, but electrons are getting sent up here as these turn into Zn2+ ions and as they enter the solution. Now over here, as electrons come over, these Cu2+ ions will turn into neutrally charged copper atoms and attach to the metal. Now look at what's happened to the charge here, okay? Now we have all of these Zn2+, but we have only a few of the SO4 2-. So after just a little while, positive charge really begins to build up in this half cell. And then over here, as the positively charged ions like this lose their charge by gaining electrons and turn into neutrally charged copper, now there are a whole lot more SO4 2- than there are Cu2+. So a negative charge begins to build up on this side. And if this positive and negative charge build up too much, the cell can't run anymore. It can't continue to make electricity. So that is where the salt bridge comes in. Let me get rid of this wire and show you what the salt bridge looks like. Here is the salt bridge. It is a tube shaped like an upside down U that in our case is filled with sodium chloride. And you can see the Na+ and the Cl- ions. Now at the ends of the salt bridge there are cotton plugs, a little bit of cotton there. And the cotton prevents the solution from just pouring out into the half cells. able to slowly pass through the cotton plugs, and here's what happens. We said that negative charge is going to start building up in the half cell over here. And so the positively charged Na plus, is going to begin moving over into this half cell to help balance out the charge. So the Na plus ions are going to begin moving in this direction to balance out the negative charge. And over here we said that positive charge begins to build up. The Cl minus ions are going to begin moving through the salt bridge to come out through the cotton and help to balance out the positive charge that builds up on this side of the voltaic cell. So over time, what we're going to see is we're going to see that the Cl minuses move in this direction to balance out the positive charge that builds up here. And then we'll see that the Na pluses begin to move to this side to balance out the negative charge that builds up here. A salt bridge helps to balance these charges to make sure that they don't build up too much, and that would prevent the voltaic cell from being able to work. Wow, so we just learned so much about galvanic or voltaic cells. Okay, so here's the basic structure of a voltaic cell. We have the zinc sulfate solution here, copper sulfate solution here, we have zinc metal and copper metal. Now, when we hook this all together, electrons start flowing from the zinc to the copper. And that's because copper that's in the solution has a strong pull for electrons, whereas the zinc has a weaker pull, so the copper wins. As electrons move from the zinc to the copper, they are lost in the zinc, so oxidation takes place, and they're gained here in the copper, so reduction takes place over here. We call this the oxidation half cell, and we call this the reduction half cell. Because oxidation is happening over here, the piece of zinc is the anode. Because reduction is happening over here, the piece of copper is the cathode. Then finally we can write half reactions for the two processes that are happening in the different half cells. Here is solid zinc losing 2 electrons because they're moving out to turn into a zinc 2+ ion, which is going to enter the solution. And then over here, Cu2+ ion that's in the solution gains 2 electrons and turns into solid copper that's going to attach to this metal right here. And then finally we can sum all of this up by writing this cell diagram or cell notation, which shows everything that's happening in a shorthand abbreviated form. Zn solid, then a line, Zn2+ aqueous. This shows the oxidation part. Then we have these 2 lines representing the salt bridge or the boundary between these 2 cells. And then we have the reduction part, Cu2+ line giving us Cu solid. So that is how a device like a galvanic or a voltaic cell uses a chemical reaction to create